Let's have a closer look at the film condensation. Assume that we have a vertical plate which is at surface temperature less than the saturation temperature, and assuming that this is the x direction and this is y direction. So if it is exposed to a vapor at the saturation Ts, now what's going to happen here is we're going to have formation of condensation. And let's assume we are film condensation. It's not just drop. We are getting a continuous film of condensation. Initially, the mass is going to be zero, like at the top of the surface. And as we goes down, we're going to see the addition of condensate that is forming on the solid surface. So we would have a development of a condensation film. The condensation film is initially laminar, and then later on, after a certain point, we see that this system becomes a little bit wavy, and then we are getting to a turbulent regime. So this is going to be the condensate film. So I'm just going to call it, this is the liquid or condensate film, or this is the liquid vapor interface. And if I look at inside that, like I can just draw the streamlines here. Let's say this is the one, and then it's getting wavy, and here we are getting to a turbulent regime. So this is gonna be the flow patterns that we are gonna see in this condensation film or liquid that is coming down. Now, they're gonna be a delta. We're going to assign that a delta. This is going to be the thickness of this condensation film that you're calling. And at any location, at any x location, I can assume, or I can measure the mass that is flowing down, m dot of x. Now the first part, just get rid of that. The first side of that, this is what we call this is laminar flow, and we refer to that as wave free. Then below that, after a certain distance or certain amount of mass that has been accumulated here, what we have is laminar or wavy regime, wavy flow. And then below that, this is what we have as a turbulent regime. For the condensations that's happening here, the way we divide this zone is based on a Reynolds number that we are defining. We call it Reynolds number of delta, and we are using delta, the thickness of the condensate, for defining that one. At the very top, delta is zero, like there is really no thickness, there is no mass, so the Reynolds numbers is zero. Then the end of the laminar wave-free regime is the Reynolds number of delta around 30. I'm just going to put it around 30. And the wavy regime is happening between 30 to Reynolds number of delta around 1800. That's the part. And then below that is where we are entering to the turbulent regime. And generally for defining the heat transfer rate or the heat transfer convective transfer coefficients, we are looking at the end of the plate. If let's say this is the length of the plate L, and we look at it to see in which regime we are locating. Now, the way that we define this Reynolds number is based on delta, as I mentioned. So this Reynolds number of delta is gonna be, we define some hydraulic diameter, dH, density of the liquid that is flowing down, velocity, some average velocity of the liquid that's going down, and viscosity of the liquid. So let's say at any of these point, if I just come and make a cross section of that and assign an average velocity. So let's say this is this average velocity that I'm just calling V of L. Then this is the way that we are going to define the the Reynolds number. Now this hydraulic diameter, dH, is hydraulic diameter, and we define track hydraulic diameter of condensate flow, and we define that as a 4 area, the cross-sectional area divided by the perimeter. So this cross-sectional area is the area that is available to the condensate flow. So let's say if we have, let's find out DH for a few geometries that you would encounter. Let's say if I have this plate, this flat plate, and there is a film of condensate forming on this flat plate. So this is the film of condensate. Now, if I look at the end of that, this is going to be delta at the bottom of this plate. And let's assume this is L. So the perimeter is going to be L. Like if I'm looking at this really bottom surface, let's highlight that with the orange. So if I'm looking at that one, this is the perimeter that has been vetted, which is L, and AC, the cross-sectional area is going to be delta by L. So this is L, delta by L. So this hydraulic diameter is going to be 4 AC over R, which is going to be delta. Sorry, 4 delta actually. It's going to be 4 delta. So this is at the location we evaluate DH. So we can evaluate DH at any of this cross-sectional area and then find out what's happening if there is a need for that. That's for the flat plate. If I have this cylinder with the diameter that are much larger than the condensation buildup around that one, so I can have this condensate film around this cylinder that is building up. So other way around. Okay. So here is the delta that we are measuring. Just call it delta here, and the perimeter that has been vetted is going to be the perimeter of this this cylinder. So for this geometry, here is going to be pi d, and the cross-sectional area is going to be pi d delta. And assuming that this is d, the other assumptions here is delta is much smaller than d anyway. So here the hydraulic diameter again is going to be 4 delta. Another geometry is a cylinder, horizontal cylinder, that we can have the condensation is just building up around the cylinder. And can have the buildup on the other side, like if that's clear. So this is, let's say, the condensation buildup that we have, and let's assume we are going to just do the evaluation of this hydraulic diameter at this point. So this is going to be delta, and if the length is L here, so the perimeter. So if I look at this cross-sectional area here, the sides that is going to be just vetted from this cylinder is going to be 2L, 1L on this side, the other L on the other side. And let's say this is D. So the cross-sectional area is going to be this 2L delta, and DH is going to be 4 delta. So for all of these 3 geometries that we are looking at, the hydraulic diameter is going to be 4 over delta. I can replace that one here. So Reynolds number that we are defining. Remember, we are defining this Reynolds number just to distinguish the flow regime and later on to evaluate convective heat transfer coefficient. So this Reynolds number delta, if you want to see at any point whether we are in which regime, it's going to be, as I was writing, dH rho L VL, the average velocity of this liquid condensate, mu L. Then I'm replacing that one by definition of this hydraulic diameter for AC, rho L VL over this perimeter times mu L. And replacing with the hydraulic diameter, let's say for this flat plate, we are going to have 4 rho L VL over mu L. 4 actually delta, they're going to be delta here too. And now when you're looking at this one, this is density times velocity times the thickness that's happening here. Or here, actually, if you look at this equation here, this term is rho VA, and that's going to be mass flow rate that is flowing down. So this one is going to be equal to 4 m dot divided by this perimeter that we have, mu of L. So this is the way that we are going to evaluate the Reynolds number. So I'm going to just write down the term that I'm defining as a perimeter is going to be vetted perimeter of the condensate area at the place that we are evaluating that one. And AC is this perimeter times delta. Anyway, you have the definition of both of them. Now, in the evaluation of this Reynolds number, we have rho L and mu L, which are the density and viscosity of liquid. These are of liquid. And VL is the average velocity of the condensate at the lower part. By lower part, I mean like at any locations that we are evaluating that one. So that's gonna be the case. Now, another things that we can do here, if let's say, if we assume HFG is the vaporization heat. So this is, let's say, the vaporization heat of unit mass of condensate volume. Then I can find out if HFG is that one, then the actual condensate, like let's say when we have the condensate, now condensate is happening at this liquid surface, okay? And this condensate is further cooling down because it's gonna reach to the TS here at this side. So what happens here is I used a modified latent heat. So the actual condensate is further cooled due to this liquid film, okay? Further cooled to TS around Tsat. So the condensation happens at the liquid surface, and that's going to be at TS, and then but that's slowly cooling down to TS that we have over there. So we define a modified HFG, we call it H prime FG, which is HFG plus 0.6 S specific heat with respect to the liquid, Tsat minus TS. And we call this one modified latent heat of vaporization for this condensate. And sometimes, like in some of the texts, you would see that they are just summing everything like HFG and call that one 0.68. Whatever terms that is remaining, CPL delta T divided by HFG, they call it Jacob's number and show it like that. So Jacob's number. And if we have that one, we can find out the rate of heat transfer. that's happening here. So the rate of heat transfer, let's call it QS or Q condensation. I'm calling QS because that's happening on the surface. It's going to be, if we have the H, AS, Tsat minus Ts. So this is going to be from the Newton's cooling law. So I need to have some average heat transfer coefficients, the surface area of the plate or the cylinders that we have, and delta T. And it's going to be equal to the m dot that we are collecting, the total m dot that is getting condensed from the vapor to liquid times this H prime Fg. So this is how we can get that one. And this Hs is the surface area that on which condensate happens actually. Condensate occurs. So don't confuse this AS with the AC that we were using for the valuation of hydraulic diameter. AC was the cross-sectional area normal to the fluid. AS is the surface that is available for the condensations. Now, from here, I can say m dot is this HAS Tsat minus Ts divided by H prime Fg. And if I use that one, I can have this Reynolds number. Remember, we were writing the Reynolds number in the form of mass. I can write the Reynolds number of delta, which was 4 m dot divided by perimeter times mu L. Now, if I replace that one by the definitions that we have here, it's going to be 4 ASH Tsat minus Ts divided by this perimeter that we have, mu L H prime Fg. And we evaluate all liquid properties at the film temperature, which is Tsat plus Ts divided by 2. And we evaluate HFG at T of saturation.